Today's chemistry lesson will be on acid-base titrations. Acid-base titrations are chemical processes that involve the slow addition of one solution of a known concentration, aka the titrant, to a known volume of another solution with an unknown concentration, aka the titrant or the analyte. The reaction continues until it reaches neutralization, which we observe as a color change. We use this technique to determine the concentration of unknown solutions. So what are acids and bases? Acids are proton donors. Some examples of strong acids include hydrochloric acid, HBr, HI, nitric acid, and sulfuric acid. Strong acids are those that dissociate or ionize completely in solution. Bases are proton acceptors. Some strong base examples include group 1 and 2 hydroxides, and a strong base is one that dissociates or ionizes completely in solution. pH is a quantitative measure of the acidity or basicity of a solution on a scale from 0 to 14. Acid-base titrations involve the reaction between the two reagents to form salts and water. Salts are chemical compounds formed by the reaction between an acid and a base, where the hydrogen on the acid is replaced by a metal or a cation of the base. So, if we have a look at this reaction between hydrochloric acid and sodium hydroxide, we see that the sodium replaces the proton on the acid to form sodium chloride, the salt. The remaining species to account for is the proton from the acid and the hydroxide ion from the base, which bond to form water. These titration graphs represent the experiment graphically. The first involves titrating a base against an acid. We observe an increase in the pH as the analyte, the base in this case, is being added to the solution. The opposite is true for the second graph, where we see a decrease in the pH as the acid is being added, which is the analyte in this particular experiment. The equivalence point is reached when neutralization is achieved, and it is a point in the titration at which the amount of titrant added is just enough to completely neutralize the analyte solution. Moving on to the equipment needed for titrations. Firstly, we have the volumetric flask containing our standard solution of hydrochloric acid. It is the titrant because we know its concentration, and we will be using it to find the concentration of our analyte. We will use this pipette to measure exactly 20 ml of the solution so that the volume is known. We will place these 20 ml into the Erlenmeyer flask where the reaction will occur. 2 to 3 drops of an indicator, phenolphthalein in our case, will also be placed into the flask to allow for us to assess the endpoint of our reaction via a color change. 2 additional Erlenmeyer flasks are required to carry this reaction out in triplicate. The next important component of the experiment is the analyte. It is a solution of sodium hydroxide and we do not know its concentration. The solution can be decanted into a beaker, so it can be poured into the burette with the help of a funnel. The burette allows for us to assess the volume of the analyte that is reacting. Here is a summary of the equipment needed. And now onto the experiment. So in preparation for the titration, we need to decant the base, our analyte, into a beaker to transfer it into the burette. We will read the initial volume and use this to find the volume that is reacting. We decanted some of our acid, our standard solution, into a beaker so that we could use our pipette to measure a set volume of 20 ml. The meniscus needs to be at the level to ensure the accuracy of the volume reading. We then place the solution into the Erlenmeyer flask where we will carry out the titration. We are almost ready to titrate. We just need to add 2 to 3 drops of the indicator, and a little bit of deionized water. The technique for titrations is to hold the tap with your weak hand from the back of it and to swivel the flask with your strong hand as we titrate the analyte into the titrant, drop by drop. The endpoint occurs when a pale pink solution has formed. The solution cannot be too dark after titrating. This is what we call overshooting the titration, and it will result in an inaccurate concentration. You have to be very careful, as you can see, but we have reached the endpoint and we can now read the final volume to calculate the concentration. We do this twice more and then we are ready to calculate. The first thing to do is to write out the reaction equation. We reacted hydrochloric acid, our titrant, with sodium hydroxide, our analyte, to form sodium chloride and water. What we know is the concentration of the acid and that we used 20 moles of it. These are the 3 volumes of sodium hydroxide that we titrated, and we need to find the average by summing them and dividing this value by 3. So we know that on average 20.1 moles of sodium hydroxide reacted to reach the equivalence point. But to solve for the concentration in moles per liter or moles per decimeter cubed, we need to convert this volume to decimeters cubed or liters, which are essentially the same thing. This equates to 0.0201 decimeters cubed or liters. The acid and the base are related by their molar or stoichiometric ratios. So we need to use the volume of the analyte to find moles. For hydrochloric acid, N is equal to Cv. We substitute the concentration and the volume that we used, which was 20 moles or 0.02 decimeters cubed, to find a value of 0.002 moles of hydrochloric acid. The molar ratio between HCl and NaOH is 1:1. So we also have 0.002 moles of sodium hydroxide reacting. We now know the volume of our analyte and the number of moles, so we are ready to solve for concentration. We substitute the moles in and the average volume reading from our burette, and we solve for the concentration of sodium hydroxide as 0.0995 moles per decimeter cubed, which we could approximate to be 0.1 moles per decimeter cubed.